In this Sallen Key analog filter tutorial, the two main topologies of Sallen Key analog filters are examined, and we would like to see how this is working, what is the transfer function, and how can we realize low-pass filter, high-pass filter, and specifically I would like to show you that depending on the selection of component values, for example 1 kilo ohm and 1 nanofarad for the main cap and resistor, then what we can get for damping factor zeta, for the natural frequency omega, and for basically the step response of low pass filter, and then frequency response, and then pole zero plot, and what we can learn intuitively from there. And I have repeated this for different scenarios involving slightly overdamped to critically damped to underdamped, and also I will show you at the end the high pass filter version. So with that in mind, let's start with the general format of Sallen Key analog filter, in which we have this kind of a structure. So imagine instead of R we have just impedance Z, let's say Z1, and this one is just as is shown here is M times R. So let's refer to this as impedance M times Z1, and then we have impedance Z2, in this case a capacitor here, so let's refer to that as impedance Z2, which if it is a capacitor, then of course it's 1 over Cs. And then we have the C over N here, which effectively, because impedance of cap is 1 over Cs, translate to N times Z2. So this means N times Z2, in which Z2 is 1 over Cs. Alright, so we have this scheme that here instead of C over N we have N times Z2. So what we can do is let's make the assumption that the op-amp is properly biased. Let's say plus minus 5 or plus minus 10 volt supplies connected, and also you can see that in this circuit the negative feedback is properly there. From the output we are having a connection back to over here, back to the negative input terminal of the op-amp, which indicates the negative feedback in this system. Effectively, this op-amp is acting as a buffer or unity gain amplifier. So let's see how this circuit is working. Okay, so with that, op-amp is not saturated because of the proper biasing and negative feedback in linear region of operation, and I can say for op-amp that is in linear region, I can say operating a linear region, I can say that virtual short is valid, which means the voltage at positive input terminal is the same as voltage at negative input terminal. Okay, so if the output is Vout, then via this wire, output is at negative terminal. So, and because of the enforced virtual short enforced by the negative feedback, V should also have Vout at the positive terminal. So this node is Vout. One thing before I write the analysis, which is a quick one, intuitively speaking, when you look at this topology of Sallen Key, when the frequency is very low, close to DC, or even at DC, S is j omega, and omega is 0 at DC. Therefore, at DC, obviously, denominator is 0 for the cap. Impedance of the cap goes to infinity, or cap is open. So that at DC, in this version, in this topology of Sallen Key filter, this is open, and as a result, what happens is there is no current that can flow through the input terminal of the ideal op-amp, because practically it has infinite impedance. So Vin, there is no current flowing through these resistors, and therefore Vin appears at positive terminal. But we know that then, because of this unity gain amplifier or buffer, Vin should be also at negative, and then Vin appears at the output. So this indicates that this topology is a low-pass filter implementation, because at super low frequency at DC we have Vin appear at the output intuitively. If the frequencies on the other hand is pretty high, so omega goes to very large frequencies, then denominator goes to infinity, impedance of cap goes to 0. Basically cap will short the positive terminal to ground, which means at large enough frequencies, positive terminal will become, the voltage at positive terminal will be 0. Therefore, as a result of virtual short, the voltage at the negative terminal also has to be 0, which means output is 0. So another indication that this is surely a low-pass filter, because at high frequencies output 0. On the other hand, intuitively for this topology, with the same argument, when the frequency is low close to DC, caps are open. When caps are open, nothing can go through the filter, so input Vin cannot go through. And because caps are open, then there is no current flowing through this resistor, so the voltage drop across this resistor R is 0, and therefore 0 appears at the positive terminal. And because of the unity gain amplifier and virtual short, if 0 is at positive terminal, 0 has to be at negative terminal, which means 0 is at the output. So all I'm trying to say is, for this topology of Sallen-Key filter, Vin cannot go through at low frequencies, and therefore at low frequency output is 0, indicating we are designing a high-pass filter. On the other hand, when the frequency goes to infinity, impedance of cap, because denominator goes to infinity, goes to 0, and because of that, these caps are shorted, and therefore Vin appears at exactly positive input terminal, which, because of again virtual short, it should be also at the negative terminal as well, and therefore output becomes equal to input, indicating that or confirming that this is surely a high-pass filter. So this is a high-pass filter implementation, intuitively speaking, and this is a low-pass filter implementation of the Sallen-Key filter. With that in mind, let's proceed with the transfer function. So I would like to find the transfer function of the general form. In this case, as you can see, we have Z1, M times Z1, and you can see that that is also valid here. So in this case, we have Z1, which is 1 over CS, and we have the impedance of this cap. And we have the impedance of the second cap to be 1 over C over MS, which means M over CS, which indicates that this impedance is M times compared to the first cap, same as what we have here. So when I'm doing the analysis for finding transfer function of the general form of, say, Z1 MZ1, and then Z2 for this one, and NZ2, so NZ2 here, then it is also applicable, whatever analysis I do is applicable for the second topology as well. So with that in mind, let's write the transfer function. So the transfer function, again, knowing that the virtual short is valid for the op-amp, I can just quickly do the transfer function. I'm going to write a KCL at this node. Let me use a different color so that it's clear. I'm going to write a KCL at this node. So writing a KCL here, let me just make sure. Okay, I'm writing a KCL here. So KCL, or Kirchhoff current law. So whatever current is coming in should be equal to the currents that are going out. So this current and also this current. So let's refer to this first one as I1, I2, and I3. So I'm going to write a KCL in the form of KCL at that node that I highlighted. Kirchhoff current law says the current that is coming in I1 should be equal to whatever sum of all currents that are going out, I2 plus I3. Okay, I'm going to substitute these for these values, but before that, one quick calculation. So because no current can flow through the positive input terminal of op-amp, effectively the MZ1 is in series with cap C. So these two guys are in series. I can write a voltage division between voltage here, which refer to it as Vx, and Vout, which appears at this node. So I can write a voltage division. I can say Vout is equal to Z2, which is instead of this guy. So it's going to be Z2 divided by MZ1 plus Z2 times Vx. Or we can write it also this way. Vx is equal to M Z1 divided by Z2. So MZ1 divided by Z2 plus 1 times Vout. So let's keep this as equation 1. Okay, now I can start substituting for this KCL that I wrote here. So I1 is obviously plus minus voltage across this resistor R, which is V in minus Vx. So V in minus Vx, and of course divide by the resistor, the impedance C1, generally speaking, not resistor Z1. So impedance C1. So that is for the current I1. Now what I can do is I need to also do the same thing for current I2 and I3. I2 is this current, which is just Vx minus Vout divided by NZ2, the impedance. So Vx minus Vout, and let me write it this way, 1 over NZ2, Vx minus Vout. And for the I3, it is the same current as this current, I3. So rather than dealing with Vx minus Vout divided by MZ1, I can do just Vout divided by Z2. So that's what I'm going to write for the I3. So Vout divided by Z2. Okay, this is helpful. Now what I can do is, from this equation 1, I also have one little conclusion, because if I just distribute Vout inside this parentheses and then do a little reshuffling, I can write Vx minus Vout is simply equal to, by moving this 1 times Vout to the other side, is equal to mZ1 divided by Z2 times Vout. So this is another variant of writing 1. So let's refer to it as equation 2, because I'm going to use it. Okay, so in this equation, what I'm going to do now is I'm going to substitute basically for Vx minus Vout using equation 2, and Vx here using equation 1. So as simple as that. I am using now a combination of equations 1 and 2, and then it becomes 1 over Z1 Vn minus, for Vx I am substituting from here, so it becomes mZ1, and I should not forget about 1 over Z1, which I can multiply to the other side. So let's do that to just clean up. So Vn minus mZ1 over Z2 plus 1 times Vout, which is substitution here, equal to, this Z1 is multiplied to the other side, so becomes Z1 over NZ2, and Vx minus Vout is simply from here, equation 2. So instead of Vx minus Vout, I'm going to write mZ1 over Z2 times Vout, and I have plus Vout over Z2, which I can factor out Vout and just write it 1 over, let's not forget Z1 over Z2. So plus Z1 over Z2 and times Vout. Let's do a little cleanup, and what we get is, let me write it here. So what we get out of this whole thing is the V out S domain, V in. So these are S domain functions, and basically this is the H of S, or transfer function, voltage transfer function for this filter, is equal to 1 over, so what we get if we just reshuffle everything around and move this part to the other side, factor V out, and then it become 1 over M over N Z1 over Z2 squared plus M plus 1 Z1 over Z2 and plus 1. So the nice thing about this transfer function now is we can use, and we can just substitute, and actually we can now extract both topologies 1 and 2 from this transfer function. Reason for that is, if Z1 over Z2, so let's put it this way, remember, just recall that Z1 is this guy, whatever we put there. So if we put cap, it's like cap there. So Z1 is this, capacitor or is this resistor? Doesn't matter, it's the first one. So if I set Z1 equal to a resistor, let's say R, as we have in the first topology, and if I set Z2 as, which is this guy, which is, there you go, Z2, if I set it as a cap, not a resistor, just a cap, then what I get is the transfer function becomes 1 over m over n RCS squared plus m plus 1 RCS plus 1. So it's nicely a second order filter, obviously. Second order denominator, as you can see, no zero, so numerator is purely 1. The denominator is a second order polynomial in S, and actually if we solve this, we will find that, and as you can see, when S goes to 0, which means when we set S equal to j omega when omega is 0, indicating DC, this component goes away, this component goes away. What remains is 1 over 1, which means gain of 1. So at DC we have gain of 1, and then when omega goes to infinity, which means then S goes to infinity, then you can see that this component or this term in denominator is the largest one, and therefore denominator goes to infinity absolute value wise, and therefore the whole absolute value of transfer function frequency response goes to 0, indicating low pass filter. So all I'm trying to say is this is clearly a low pass filter, second order, the Sallen-Key filter, and then from this low pass filter, what we learn is interesting outcomes. We learn that for example, if I set, generally speaking, if I set R equal to 1 kilo ohm, C equal to 1 nanofarad, so as a reference, if I set this to 1 kilo ohm, this R, as I showed you, so 1 kilo ohm by R meaning this R. And if I set the reference cap here as 1 nanofarad, then depending on what I do in terms of the value of m and n, I end up with having different scenarios realized, because the zeta or damping factor of the circuit and the natural frequency omega n are functions of zeta, mainly just m and n, and the omega n is function of 1 over RC times the square root of n over m. So we can adjust the value of that. I'm going to show you quickly, but before that let me also show this one, that if on the other hand we go with Z1 equal to 1 over CS and R to Z2 equal to R. So by that I mean the second topology. As you can see, Z1, so Z1 is 1 over CS now, is a cap instead of a resistor, and the Z2 is a resistor instead of a cap in the first topology. So if we go with this scheme as this choice indicates, now the transfer function Z1 over Z2 is not RCS, which used to be, is going to be actually 1 over RCS, because Z1 is 1 over CS, Z2 is R, so we're going to get us 1 over RCS. Now, therefore, the transfer function become in the form of the denominator becomes in the form of m over n 1 over RCS squared, and then the next term, this one, becomes m plus 1 over RCS, and then plus 1, and then when we reshuffle everything properly, the new transfer function, when we clean up, the new transfer function looks like this: R square, C square, S square, and then we have RC, so RC S squared, so RC R squared, C squared, S squared, plus m plus 1 RCS plus m over n. This is clearly a second order high pass filter, And you can, aside from intuitive analysis at the beginning that I did to show it's a second order high pass filter, you can see what's going on. If I set S equal to j omega, at DC omega is 0, frequency is 0. When the frequency is 0, denominator is some non-zero value, because this goes away, but m over n remains. Then numerator actually is set to 0. So the transfer function is 0, meaning nothing goes through this filter DC-wise or low frequency-wise. But then when omega goes to infinity for large enough frequencies, this component, they don't matter compared to this that is a function of s squared and grows rapidly given large omega. And then the whole transfer function converges to RCS squared divided by RCS squared, which means 1. So all I'm trying to say is it's clear that in this case, it's clear that the transfer function is a high-pass filter, second order, that is implemented. Okay, so now we know the source of these two topologies or realizations of the Sallen Key analog filter for low-pass and high-pass filter. Let's examine the choices that we have. So when we are designing a Sallen Key filter, we need to be careful. For instance, in the design that I'm presenting here, if, as an example, if we set, let's put it this way, I'm going to just draw it here. So V in, and then in this example, I am selecting this one as 1 kilo ohm, and I am selecting this one. If we go with 9M, which means this one is 9 times 1 kilo ohm, so it's going to be 9 kilo ohm, and then we have a cap. But this cap is our reference, so this is C, and C is selected to be 1 nanofarad, so this one is 1 nanofarad. And then we have connection to the op-amp, a decent, depending on the target speed or target frequency, the proper op-amp with the proper slew rate and proper bandwidth can be selected from either analog devices or Texas Instruments op-amp. They have a good selection depending on what frequency or a slew rate you have in mind, or even, let's say, what sort of a noise performance a designer has in mind. So let's consider this then buffer, and then at the output we have V out. So this is the form of our Sallen Key filter, and it's a low-pass filter in this case. So second order Sallen Key low-pass filter. And of course we can cascade more of these blocks one after each other. So if you repeat cascading, you can realize higher order filters like order 4, order 6, and so on and so forth. But let's say in this case this is 1 nanofarad, but then if we select n equal to 1.8 in this example, then it means this second cap will be C over 1.8. So it will be 1 nanofarad divided by 1.8. Okay, so if that is our selection, then zeta, or the damping factor of the filter, becomes roughly 2.24. So 2.24, which means we are dealing with an overdamp scenario, because zeta larger than 1 means overdamp, and in the overdamp design, the step response, so this one is a step responsive filter, you can see that it's nicely starting from 0 value at the output. So this is amplitude of output voltage wise. So what happens at the input V in, it is a step like this, so 0 to 1 volt, and we are tracing that at time t equal to 0 that it jumps to, V in jumps from 0 volt to say 1 volt. Then how the output is tracking that, and this is the output moving up from initial state of 0 volt at time 0, the x-axis is time, y-axis is the output of the filter in voltage, so volt out. This is V out, and you can see we go to 1 volt for V out, and the ramp up is pretty nice because it's overdamp. There is no overshooting like this, and because it's overdamp. And then you can see from 0 we nicely asymptotically go, output goes to get to 1 volt, similar to where the input is standing. So output reaches to input in this low pass filter after some time, in this case after about let's say, roughly 0.5 10 to the minus 4. 0.5 10 to the minus 4 seconds, which means about 50 microseconds. So we can say output almost asymptotically reaches to the value of the target value of input after about 50 microseconds. So that is the nice response of an overdamped filter for the frequency response. So for the frequency response, you can see that based on the values selected for M and N and given R and C selected basically for this circuit, then omega n or natural frequency is 4.5, about 450 kiloradian per second. And that's sort of obvious. I mean, take a look at the pole zero plot. It's overdamped, so one of the pole is much closer to, so x-axis is real value of, so this is S domain, pole zero plot, S domain. So this is the real part of S, and this is the imaginary part of S. So you can see that the imaginary part is 0. It's an overdamp, so poles are just pure negative real values. So this is negative about 100,000 radian per second. So this is about 100,000 on the x-axis, and this one is further away on the x-axis, is nearly about negative 2 million radian per second. There you go, negative 1.9 million radian per second. So these are pure negative real pole indicating an overdamp response, and you can see that the frequency response at the beginning is just not at the beginning. Frequency response at low frequencies like 1 radian per second up to about close to 10 to the 5 radian per second is flat at 1, indicating that response of filter is just 1. Whatever comes in these frequency ranges at the input of the filter will appear at the output of the filter without change. But then starting from about 10 to the 5 radian per second, when we are getting close to omega n, then filter starts dropping. And that's reasonable because the first pole is at about 100,000 radian per second. So as we get close to 100,000 radian per second, the drop in the response starts. We know that for every pole, ultimately we have to get 20 dB per dB drop in magnitude response. This is the magnitude response per decade, which means per 10 times increase of frequency. So initially you can see from 10 to the 5 radian per second to 10 to the 6 radian per second. As we increase frequency 10 times, we can see that the magnitude drops by 0.1, which 20 log base 10 0.1 is negative 20 dB. So exactly matching what we expected for one pole. But as we get close to the second pole, which is at around 2 million negative radian, so 2 million, which means roughly here. This is the second pole, so P2. And this is roughly the first pole, P1. So after we cross P2, the slope of this drop actually goes to twice, because now we are dealing with 2 poles, 40 dB per decade. So there you go. Over here, now slope is dropping faster. So if after this point, if we start going 10 times frequency increase, then the drop will be, instead of 20 negative, will be another 40 dB drop. So we get to 40 dB per decade drop. Every 10 times increasing frequency, we drop the magnitude response by 40 dB. Phase, as expected, start from 0 degree phase. So basically filter doesn't change the phase of incoming sinusoid. So at the input of filter, if at the input of filter you apply a sinusoid Vin, and let's say Vin is in the form of a amplitude, let's say cosine omega t, whatever amplitude, let's say amplitude 1, just to make it easier. So V in 1 cosine omega t and with no phase, phase 0. Then what happens is at the output, V out is if omega of this sinusoid is in this range, is in this range, then output is the same amplitude as input. So one amplitude comes in, one amplitude goes out for this low pass filter, and then phase in this frequency range, phase also remains 0 unchanged. So filter doesn't add or subtract anything to phase. So output is exactly cosine omega t plus 0 as well. Now if we start crossing a point that is about 0.1 p1, like phase body plot, then we start dropping the phase. The filter will start reducing the phase, and for every pole it reduces the phase by 90 degrees. So see, by the time we are done at about 10 times p1, we are down in phase from 0 to about negative 90 degree. So this point. By this time, given that the second pole is far away, now we see the impact of the second pole kick in, and we drop another 90 degree because of the second pole, and by the time we are done with the impact of the second pole, we are roughly at about negative 180 degree. So depending on where we are on the frequency of the axis with respect to the frequency of sinusoid, it will experience different type of phase impact by the filter. So filter will either not change the phase or reduce the phase by some value between 0 and negative 180, depending on the frequency of sinusoid. Okay, so let's move on quickly. If we just adjust the M and N while keeping the R and C at 1 kilo ohm and C is 1 nanofarad, if we now adjust the M and N so that we keep the circuit as it is. So what I'm doing is keep this one as it is, keep this, let's say we are not even changing M, I'm gonna keep M as 9, but the only thing I'm changing is N. Instead of 1.8 is reduced to 0.37. If I do that, basically this remains 9K, this remains 1K, this remains 1 nanofarad, but the only thing that changes in the circuit will be this C over the second cap is going to be C over 0.37. So that's the only change that now I'm applying. So basically what I'm doing is I am increasing this cap. I'm increasing this cap that is positioned here. So with that, what happens is it becomes slightly overdamped now, and as a result of a slight overdamp, what happens is we don't, because it's slight overdamp, we are not seeing any. Because of a slight overdamp, we are not seeing any major change in the step response, and frequency response remains almost the same. The only observable change is the poles that are like this at let's say 100,000 radian per second and about 2 million radian per second are now getting closer to each other at around negative 2.4 million radian per second. Sorry, 240 at about 240,000 and about 170,000 radian per second. So this pole moves in, this pole moves in, and they become like this. But we don't see that much of a change because in the frequency and the step response, because zeta is not that much change in terms of the fact that it is still overdamped. Now, of course, omega n is changing. That's one thing to notice. Previously, you can see that at 10 to the 5 radian per second, we had a slight drop. Now, because natural frequency was 450,000, now at 200,000 radian per second, we can see drop is more because drop starts earlier. If I go to critically damp, zeta 1, and then again we see that not much of a great change in terms of step response, except maybe it is converging faster. So instead of let's say 50 microsecond, now it's happening at 40 microsecond. So this point is 40 microsecond. So at 40 microsecond we get to steady state. So basically we get to a steady state faster as we start reducing the zeta. That's the benefit we get, but we need to be careful. So how do we get there? I further reduces n from 0.37 to 0.36. That's what I did. And then omega n remains almost the same because nothing changed that much. But now what happens is exactly as at 0.36 n, zeta is exactly 1, system is exactly critically damped. By that we mean the two poles that were getting close to each other, as I talked about, now completely converge on each other. And these two keeps getting close, and then they converge at exactly negative 200,000 radian per second. These are two poles. So we have two poles on top of each other here. Two poles on top of each other. And in the pole zero plot or pole zero map. This is critical damping. And now beyond this point, if I keep reducing n further while keeping m and RC constant, I get to n 0.18. And in this case, zeta or damping factor becomes 1 over square root of 2, which is 0.707. Because it's less than 1, it means we are slightly underdamped. It's not a lot less than 1, just slightly less than 1, slightly underdamped. And because of that, now we are saying while we get to initially to the value 1 faster, but then the penalty we are paying is a little bit of a overshoot. So that is the meaning of underdamping. So there you go. But it's just one shot. So after one of overshoot, we get to steady state. So it's on the order of again 40 to 50 microsecond with an overshoot, but then we rise faster. Okay, so the frequency response, you can see that omega n is further down from 200,000 to about 140,000 radian per second. And now the poles are shifting outward. So the poles were used to be completely real. Now they are moving outward as complex poles. And they are now at 100,000 omega radian per second. And if we keep doing this to low pass filter as shown here, by further reducing n, we see that we get to low pass filter that is now seriously considerably underdamped with zeta 0.224. And then again repeating the omega n for low pass filter. This time omega n is further reduced from what used to be 450,000 to now 10 times less, 45,000 radian per second. As you can see that, there you go, at about 45,000 radian per second, because of the and in this case we have also an overshoot, serious overshoot in the frequency response as well. Not only overshoot in time and underdamping in time with multiple oscillation, we also have overshoot in frequency. Phase response 0 to negative 80, and you can see that for the two poles, they are now actually reduced omega n value wise as expected. So here we had in the previous scenario 100,000. Now we are 45,000 for omega n. And then if we go to high pass filter, everything is exactly the same, except now in high pass filter version, rather than having R here, we have cap, we have resistor, and we have resistor. So with that, it becomes a high pass filter. Formula for zeta is the same for both high pass and low pass. So zeta is the same formula as a function of m and n, and the only thing that changes for the formula is for low pass filter, omega n is 1 over RC times the square root of n over m, but in high pass filter omega n is 1 over RC square root of m over n. So because of that, we can see this response. I hope that this example is helpful in the sense that showing how we can realize low pass and high pass Sallen Key filters, and how we can control the damping factor in the design depending on low pass, high pass, and how we can control having overshoot or undershoot, and how we can also control not having or having the overshoot in the frequency response as well. So in this case, in the low pass filter version, when we are seriously underdamped with zeta 0.2 roughly with this selection of m and n, then you can see that omega is at 45,000, and overshoot is roughly jumping from value of 1 to about a value of, let's say, maybe about 3, which means about 5, 6, 7 dB. So with that in mind, then just for omega n for the high frequency one, we are talking about 22 mega radian per second in that range for the same selection of components. All I'm saying is, in the last example, when I'm having considerably underdamped scenario for low pass filter and high pass filter, for the same value of components selected, then the realization, while represent the same type of frequency domain overshoot, the value of frequency at the overshoot point is completely different for the low pass versus high pass. So we need to be careful what version we are implementing. I hope this example is helpful in terms of a tutorial walkthrough of the Sallen Key analog filter design and how we can realize low pass filter and high pass filter using Sallen Key topology.